Heterojunction of graphene-based composites for membrane application in COVID-19 pandemic mitigation. This project is part of the PH Cares program Technical Battle Against COVID-19. I am Marinette Vega from the Material Science and Engineering program. With me in this project are Drs. Alan Yago, Marlon Conato, and Michelle Regolacio of the Institute of Chemistry. The students who are working on the project are Joven Angeles, Ronnie Andig, Conan Casalme, Romina Ramos, Miguel Pulido III, May Tumangil, Joybel Lopez, and Vida Saison. COVID-19 pandemic has greatly changed the world since its initial infection in 2019. We have been trying our best to live with the virus for over 2 years now. Our everyday lives have changed to prevent the virus from spreading. Here are some of the ways to prevent the transmission of the virus. Vaccination has proven to be effective in fighting against the severe symptoms that accompany the infection. Frequent hand washing, continued strengthening of our immune system, social distancing, and mask wearing all contribute to slowing down the transmission. Masks can significantly reduce transmission of the virus. In fact, studies show that transmission was 7.5 times higher in countries that did not have a mask mandate. Masks accomplish this in two ways: by controlling the source of the virus and by protecting a potential receiver. COVID-19 or SARS-CoV-2 always attaches to aerosols and droplets produced by breathing, talking, coughing, and sneezing. These respiratory particles contain mucous proteins that reach a size up to 500 microns. When respiratory particles has the size of 5 microns to 100 microns, they are considered as aerosols. Larger than 100 microns are considered as droplets. Particles of this size can remain in air for about 10 minutes. Our role as scientists is to understand this mechanism underlying the problem and study potential solutions to stop the problem. The challenge that faces us now is to improve mask material design in two ways. First, to reduce the pore sizes of the masks to prevent particles having the size of tens of microns from passing through. And second, is to increase the electrostatic absorption at the surface. As candidate filler materials, we chose graphene and its derivatives. Distinct properties of graphene that made it significant in researches include high surface area, outstanding mechanical strength, unmatched thermal conductivity, and supreme electronic properties. They also have highly tunable functional groups. The second filler material is a metal organic framework composed of zinc ions coordinated by 4 imidazolate rings or framework. This is ZIF8. Due to the complex structure of ZIF8, it contributes to the reduction of the pore sizes. The two components will be combined in an optimized ratio. We are using a polymer blend to bind the components together and produce the fibers. The resulting fiber may be used as a middle layer to the existing 3-layer or 5-layer masks that are commercially available. The components that we synthesize may be further functionalized to enable in situ breakdown of the spike proteins. This is a task for future work. Our hope is that by taking advantage of advanced materials design, transmission of pathogens such as COVID-19 and its variants will be slowed down and eventually be stopped. This project would not be possible without the help of the following: DOST Pictured for the generous funding. Institute of Chemistry and National Institute of Physics, UP Diliman, for the use of laboratory. Thank you for listening.